Hi ladies and gentlemen, welcome to Lesson 3. We're going to take a look at Strang, Section 1.3, which is really an introduction to matrices. I know many of you are at least a little bit familiar with matrices, and this begins our kind of in-depth understanding as to what matrices are and the beginnings of how we can use them. So let's just jump right in. We have here the beginnings of the definition of a matrix and a conversation about rank. So the way matrices are set up, in general, we talk about A being an M by N matrix, where the M is the number of rows, and that's always by the number of columns. And that's the reason for the RC cola that we're using here. M and N are not unique. You will see some texts or references that will use P by Q. It's always the same. It's always rows and then columns. That's the standard way to reference the dimensions of a matrix. The conversation about rank we'll have a little bit later in today's lesson. So a couple of ideas about matrix multiplication are provided here. So we have A times X, that's a matrix times a vector, and he provides us the understanding about matrix vector multiplication as dot products between rows and columns. We're going to really get into this more in the next lesson, but he brings it up here, so I'll provide a brief conversation as an introduction. Also, he talks about linear combination of the columns of A as a different means of thinking about multiplication. We've already considered both of these, and we will review that in just a moment. Column space of A and A is a really important idea, and that is one of the fundamental pieces of today's conversation. It's really straightforward. It's all combinations of the columns of A. So whatever size A is, we look at the columns and we look at all possible linear combinations, and that is what the column space of A is equal to. The column space is a vector space. It's infinite in size. It has an infinite number of vectors in it. And what we're thinking about is just how do we construct this given any generic matrix A. The final thing we're going to talk about today are rank 1 matrices. Just a brief introduction. Again, we will build more on this next time. So let's start with the example that we had previously where we have 3 equations and 3 unknowns. This is, we have 2 unknowns, 3 equations and 2 unknowns. And we talked about writing this in what Strang calls the row way. And you remember we had 2 other ways to represent a system of equations. One of them is the column way, where we take x1 and we multiply times the vector, which is its coefficients, which in this case would be 2, 1, negative 3. And then we add to that x2 multiplied times 3, negative 1, 1. And then finally we set that equal to a vector, which is negative 3, 2, negative 2. And this vector representation of the equations is what Strang calls the column way, because we're really focusing in on the coefficient vectors, the column vectors for the coefficients, as well as the right-hand side vector. And then finally we have the matrix way, where we write down the columns associated with the coefficients for each unknown. 3, negative 1, 1. This is a matrix now, which we see as a 3 by 2 matrix. And we're multiplying that times the vector of unknowns, x1, x2, and that's equal to the right-hand side vector, negative 3, 2, negative 2. So this is where the matrix vector product conversation is coming in section 1.3. We're really looking at this matrix down here of coefficients multiplied times a vector of unknowns. And this is very common for us, and we'll see this quite a bit as we look at solving systems of equations. And remember, he calls this the matrix way of thinking about a system of equations. This is the matrix way. And we will deal with this because now we're really talking about the matrix and we want to understand its column space. Before we get to that, let's just take a brief look at, you're going to read through this, of course. This is a brief conversation about some special matrices that are named. We have the identity, the diagonal, the triangular, and the symmetric matrices. All of these are reasonably straightforward. I'm going to spend just a moment talking about triangular matrices because it's not necessarily clear what he's talking about here. Triangular matrices are matrices that have zeros either above or below the main diagonal. So the main diagonal for a matrix is the diagonal that starts at the 1, 1 position in the matrix and then works its way down 2, 2, 3, 3, 4, 4, etc. The matrix doesn't necessarily have to be square to have a main diagonal. It's always that diagonal that starts at 1, 1 and comes down, but oftentimes we're talking about square matrices. So a triangular matrix is a matrix where we have zeros either above or below that main diagonal. On the other side, the numbers don't have to be zero. So in this case, we have non-zero numbers up here above, so this is called upper triangular. An example of lower triangular, so if we look at a lower triangular matrix, then we're looking at something where the values on the main diagonal could be anything, and then down here we have possibly non-zero values, but all the values up here are zero. That would be a lower triangular matrix. So it's not just triangular. We have upper triangular and we have lower triangular, and we'll see a lot more of that when we get to chapter 2. Continuing on then, we have this conversation about the row picture and the column picture, similar to the row way and the column way of thinking about the system of equations. And he goes through and talks about the matrix vector multiplication down here in the row way, which is a set of dot products. So let's come back and make sure that we understand how the system of equations is represented in each of these different ways. You'll notice here's our first equation. And we're accustomed to looking at equations in this manner. We just have this set of mathematical expression with an equal sign in it. Well, that same equation exists in the column way when we think about this top set of numbers. So we have x1 times 2 plus x2 times 3 is equal to negative 3. And that's exactly the same as what we have here. Those two are identical. And then finally in the matrix vector multiplication, we have the same thing. This row right here is the first equation. So the equations are always going to show up as the row. And let's just talk about this. This is the row way of thinking about the dot product. We're going to take x1 and multiply it times 2. And we're going to add that to x2 multiplied times 3. And then that's going to be equal to negative 3. And so we have that top equation. And every row is an equation. These all line up, of course. We could take a look at, I'll do it in blue, we could take a look at this equation. And of course, that equation meshes up with the second row here and the second row here, understanding that we're going to take x1 times 1 and x2 times negative 1. We have that dot product. We're going to add those together, and that's going to be equal to the 2 on the right-hand side. So that's what he's talking about with respect to this multiplication, and we're going to leave you to take a look through this information. What we want to do then is take a look at the other way of thinking about matrix vector multiplication, and I've written it out here. All I've done is rewritten the column way that we were talking about, and I've just done it so that we can run a demonstration of what it looks like to think about the matrix A and its linear combinations. The matrix that we have up here, remember, is the coefficient matrix. This is the matrix 2, 1, negative 3, 3, negative 1, 1, and what we're interested in from a column space perspective is what are all the possible linear combinations of these two vectors. We already saw something like this in the very first lesson of the class. Let me pull up a MATLAB graphic here and show you. What I have is I have the red vector, which is the first column of A, and then I have the green vector, which is the second column of A, and then I have the blue vector. And what's important for us to realize is when we're solving a system of equations, the question that's in our mind is really, hey, can we make a linear combination of the columns of A and get it somehow equal to the right-hand side vector? So another way of thinking of that is the right-hand side vector in the column space of A? Let me run this simulation for you. And so we see, again, I'm taking random x1 and x2 values to create the black vectors. And it certainly seems like I should be able to find an x1 and x2, which is going to give me a linear combination of the red and green vectors that's equal to the blue vector. It certainly looks like we're close over here. However, this is an optical illusion, as we saw previously. We know the linear combinations of these two vectors are going to be a plane. We saw that previously, and the question is, does the blue vector lie inside the plane? And we could see clearly that it does not. So it turns out that there is no way for us to reach outside of the plane and get to this blue vector. There are no x1 and x2 values such that we can solve this system of equations. And that's similar to what our intuition tells us. Generally, if we have 3 equations and 2 unknowns, we wouldn't expect to be able to find a solution. Maybe we can, but there's no reason to think that in most situations we would be able to do that. And certainly in this situation, we can't, because that blue vector does not lie in the column space of A. And this is the conversation that he's having here with respect to the multiplication conversation as rows, but then as the linear combination of columns. And he gives us a bit of a graphic down here to have this conversation. Let's take a look at a different example. So in this case, what we're going to do, so this is important to read through everything here that's on page 20. We're leaving you to read through and take a look at the terms that he's using. He's talking about independent vectors, and then he's talking about dependent vectors. The opposite of independent is dependent, and then he says these 3 columns are dependent. I just want to give you again another example of what it is that he's referring to. Here's a different matrix A. It's different than the system of equations that we were talking about previously, and let me pull up the graphic. All right, so what we have here are the 3 columns. We can spin this around a little bit and we see these 3 columns of the A matrix here. And again, we'll just take a look at randomly selected constants which are being multiplied by each of these vectors, and we want to see what the column space of A looks like. What does a representative sample of the linear combinations of the columns of A look like? And what we see is this is a spiky ball. It appears that we could pretty much represent any vector in R3 as a linear combination of these 3 columns. And that is in fact exactly the case. It turns out here that the column space of A is equal to the vector space R3. We can get to any 3-dimensional vector by taking a look at a specific linear combination of these columns. And in fact, that would give us a problem. We would have something that would look like AX equals B, where we would be given B in R3. Remember, this is the symbol here for element of. So given some vector B that's in 3-dimensional space, the question is, what would be the coefficients for the different columns of A in order for us to represent that vector? And what we saw from the graphic is we can do that for this specific A matrix. Now let me make a slight modification to this matrix. All right, so I've made a modification to the A matrix and I've called it B. What I've done is I've taken this last column and I've replaced it with a different final column. And graphically what we end up with then is this right here, which we can take a look at. We have these 3 vectors, and the question is now, what is the column space of B? Do I still have when I take a look at the linear combinations of the columns, do I still have coverage for all of R3? And as we can kind of see here, we actually don't. These vectors only cover, even though I have 3 vectors, they only cover a 2-dimensional vector space in R3. They only give me the plane. And that's because the vectors, the columns of B, are linearly dependent. This is an example of linearly dependent vectors. This is a situation where I can write at least one of the vectors as a linear combination of the other vectors. And that's what I have here. One way of seeing this is relatively straightforward. We can see that the vector that we have here is just the first vector. So it's the first column of B minus the second column of B. And that's how I came up with this third column. I just took the first column minus the second column. And because we have this relationship between the columns where I can write one as a linear combination of the others, then these are linearly dependent vectors. The columns up here in A are linearly independent. There's no way to write one of them as a linear combination of the others. So this is this idea of linear independence, or what we often refer to just as independence and dependence for a set of vectors. And so he talks about that here in 20. We're going to leave you with this idea of the column space of A is all combination of the columns. We have a specific word for that, and that word is span, right? So the span is all possible linear combinations. It's a definition that he provides down here at the bottom of page 21. So take a read through all of 20 and 21. Take a look at the specific examples that he provides, and then down here we can see his definition for span, which is all linear combinations of a set of vectors. So given a set of vectors, when we consider all those possible linear combinations, that's span. He also provides for us an example here with the matrix A5, and he says, hey, the columns of A5 are linearly dependent. And he gives us this relationship. The relationship is the fourth column is equal to a linear combination of the other three columns. My question to you is it possible for us to write the first column as a linear combination of the other columns? In other words, is it the fourth column that's the bad column that is making this set linearly dependent? Or is it just the collection is linearly dependent, and there are many different ways that we could write one of the columns as a linear combination of the others? I'm going to leave that for you to think about. So here on page 22, he provides some examples associated with rank. And then he gives us some words down here that we're going to take a look at the definitions of. So it turns out that rank is associated with a matrix. So we have the rank of a matrix, for example, rank of A, and the rank of A is equal to the number of linearly independent columns. So this is equal to the number of linearly independent columns. And this references back to the conversation he's having up here, where he talks about the possibilities for a 3x3 matrix. We could have 3 independent columns, 2 independent columns, 1 independent column, or if the matrix was all zeros, we would have 0 independent columns. So this number of independent columns is actually equal to rank. It would be the rank of the matrix under consideration. Another term that he's throwing out for us is basis. So a basis is a set of vectors. The basis is a set of vectors, and we'll talk more about what this is. It's really a set of building blocks. Remember, we use the term standard basis for I hat, j hat, and k hat. So if we consider the set of vectors I hat, j hat, and k hat, it is a foundation from which we can build all vectors in R3. That's what a basis is. It's a set of vectors that we can use to build other vectors. He puts out a couple of other items for us to consider. Let me highlight them here. A equals CR. This is our first matrix decomposition. We'll talk about it next time. And then also this idea of row space. It's easy for us to visualize and think about the fact that, hey, if a matrix has a column space, which is all of the linear combinations of the columns, We also could have a row space, which would be all the linear combinations of the rows. It's exactly the same type of idea, except we're using the rows instead of the columns of the matrix. The final thing under consideration here in his section 1.3 is rank 1 matrices. For the most part, we're going to leave you to read through this. Let me just highlight a couple of items. What does it mean for a matrix to be rank 1? That means it has only one linearly independent column. So what does that mean about all the other columns of the matrix? It means that they have to be scalar multiples of that one column. And that's what he's talking about here. When we have a rank 1 matrix, all the rows are multiples of a single row. That's true of the columns as well. All the columns are multiples of a single column because it's a rank 1 matrix. It turns out that rank 1 matrices are very useful, quite powerful. We'll talk more about them next time. But as for today, just take a read through this and make sure that you're familiar with the idea of rank 1 matrices and how that relates to the column space and, as it turns out, the row space for matrices. That just leaves us with our set of questions here. These are the questions for the third lesson, having to do with column space and rank, and then linear independence and linear dependence. Again, we haven't provided formal definitions for these things, but we're just using them so that you become more familiar with them. We will provide formal definitions in a few lessons. Thanks, and we'll see you in class.